Welcome everyone to the Networks seminar. Our first speaker of this new seminar is Cristian Bodnar from Microsoft Research, and he's gonna tell us about sheaf-based approaches to graph neural networks. Go ahead, Cristian.
All right. Hi everyone. Thanks for having me. Most of the stuff I'll talk about today is stuff I did during my PhD. I'm no longer kind of actively working on this, although I'm still somewhat working on graph neural networks these days. But hopefully you'll find this interesting. I think probably I can claim the title for the most weird introduction you'll see to graph neural networks after this talk. It's not how you'll typically see them presented, but hopefully, at least if you've seen them before, you'll see them a bit differently now. Or if you haven't seen them before, hopefully it will make you curious about them and you can read up more. All right, so let's just get started. So first, some fundamentals. So I think this would be the normal introduction you would see to graph neural networks. So I just put a slide on this. So as I said, not to make it too weird. And in particular, in all this talk, I'm going to talk about a very specific family of graph neural networks, which are called message passing graph neural networks. So these are just some models. As you know, neural networks are kind of used everywhere in machine learning these days, and graph neural networks are one of the, or maybe the primary paradigm to kind of process data that is sort of attached to graphs or networks more generally. And for now, we're just going to assume we have some node features. So you have a graph or multiple graphs potentially, and each of the nodes in this graph have some features. These features are just some vectors associated with each node, and we want to kind of process these data, both the features and the graph structure, to make some predictions. So for instance, we want to classify the nodes. So for instance, if this is some sort of email network, we want to classify users if they are spammers or non-spammers and things like that. Or if these are, for instance, molecules, maybe you want to predict what's the solubility of this molecule, which is represented by a graph. So these are some common applications. And most of the graph neural networks fall in this message passing family, and they kind of look like this. And can be framed in the following framework. So for each node in your graph, it will receive a message from its neighbors, and this message will basically be kind of a processed version of the neighboring features. So how do you process them? There'll be some sort of neural network in there, but essentially you get a vector from all your neighbors that's a function of the neighboring features, and then you aggregate them. So this is the first step. There's this aggregation step. So for instance, you sum all the features of the neighbors. That would be a very simple aggregation. And after that, you perform an update step, which takes this aggregated message, which you see here in green. This is just a vector. And you take the features, the current features of that node, and you pass them through what's called an update function, and kind of it merges these two vectors together, and you get a new feature for this node in the middle. So now it's kind of drawn in orange to signal that. And this happens for all the nodes. Here I'm just showing only one node, but this happens for all the nodes. And this is one layer essentially of message passing neural network. And then what we're going to have is multiple layers of this. So you can repeat this process for as long as you want to compute better and better representations for each node. And then you can do something at the end with these, like classify the graph or the nodes and so on. So that's kind of the framework we're going to operate in for the rest of the talk. Now, okay, this is gonna get quite hardcore into the subject, and we're gonna jump from this kind of very simple introduction and see how these objects, these graph neural networks, are related to these things in topology that maybe many of you in this seminar will be familiar with. So these are these objects called sheaves. They're also in algebraic geometry, so I guess they span over multiple fields in mathematics. Here, a little technicality. There's kind of two different objects. There's pre-sheaves, which are more general, and sheaves that satisfies certain extra conditions. The magic is that on when you look at these objects on graphs, they're pretty much the same. So I'm just going to use them interchangeably. So and I'm going to define them in a second. But if you see pre-sheaves or sheaves, don't get confused about that. It's the same thing for our purposes here. Okay, so how do these things look on a graph? What are these things? So it's very simple. It's just kind of the graph with some data on top, basically. So if you have a pre-sheaf over a graph, it will consist of the following things. So for each node, you'll have a vector space, which is kind of what this drawing is meant to show. This square here, that's the vector space of node V. And I should say all these vector spaces have an inner product as well. I haven't said it in the slides, but assume there's an inner product somewhere in there. Then the second component, we're also going to have a vector space for all the edges in the graph. So that's this square in the middle that you see here. And then we also have some linear maps that connect kind of incident vector spaces. So whenever a vertex is incident to an edge, there will be kind of a linear mapping between their respective vector spaces. So this is how a pre-sheaf or a sheaf on graphs looks like. So it's a very simple construction. Another way to look at it is kind of as a map between two worlds. So on the left, you kind of have the graph structure. So this is the same graph you saw on the previous slide, where you just have two vertices and they're connected by an edge. And I've kind of drawn them in this way, right? And this is kind of a way you could draw the graph in just an equivalent way. And you kind of map this structure into something else, into some other kind of structure. And this other kind of structure we map it to are vector spaces and linear maps. So all the nodes and edges of the graph get mapped to these vector spaces. And whenever you have these incidence relations shown by an arrow here, that's mapped to a linear map between these two things. So it's kind of like a translation process from graph structure to vector spaces and linear maps. And this is how category theory kind of looks at this thing. So this is kind of the category theoretic perspective of things. But I'm not going to get into that, just more in case you're already familiar. Now, something interesting you could ask is like, okay, we have a graph on the left, right? But what happens if we replace this world on the left side with something completely different? Like let's choose a completely different different object. And that would be a group. So let's see what happens. So we get something like this. So here I've just drawn some abstract group on the left in a kind of sort of similar way. Now we kind of, instead of having two nodes, we kind of have just one node, this star we have in the middle, and then we have just arrows. So the arrows are the group transformation. So for each element G, there's like an inverse G to -1. There's a neutral element E, and there's also other elements which I haven't drawn. So there's just a way to draw the group. So now let's perform the same kind of translation to vector spaces and linear maps. So if we map this star, which is kind of the only node we have now, we have a vector space, which I've drawn here in blue, right? And now basically the linear maps, for each transformation in the group, we're going to have a linear map, a matrix, and this will be invertible matrices. So this is kind of just a group representation. So for instance, if this group is like some rotations in 2D, right? We map them to these kind of rotation matrices. And here I'm just giving you an example. If I have a vector in this vector space, and I apply this matrix f of g, which just rotates v by 90 degrees, you get this new vector. So that's just something that we recover. So essentially, we recover a very similar thing, or like very familiar thing, which are these kind of group actions and group representations and things like that. So yeah, in this sense, we're going to generalize now this kind of idea of group actions. So we can kind of go back to the previous picture and ask ourselves, okay, what is the equivalent of a group action in the previous world we were in, right? So let's see what happens if we do that. So if we go back to our previous picture, this is just the graph we had before. And let's see what will be the equivalent of taking these actions. So let's look what we actually did before. We kind of treated these group elements like kind of buttons, right? If I press one of these buttons, or arrows if you want, right? If I follow one of these arrows, I'm going to look up the corresponding matrix we mapped it to and apply that matrix. There's kind of like buttons to act on the vectors in this vector space. So it's kind of a similar thing here. Now we can look at these arrows, these incidence relations between vertices and edges, and we can kind of treat them as buttons. So, you know, if I press on this button or follow this arrow, I can kind of move a vector from this vector space of node V to the vector space of node E. So I can kind of do these sort of actions to move vectors around. So for instance, you can define a left action. So basically you use these arrow, the first arrow on the left, to act on some features at node V, or some vector in this vector space at node V. So how do you do that? Exactly as before, you look at the corresponding linear map. So it's this map here. Hopefully you can see the cursor. Yeah, so you look at this matrix here, and you just and you just apply it on this vector, and then you get another vector in the vector space of the edge. So you could think of this as an action. I've just moved some features from the vector to the edge. You can also go the other way around, assuming you have enough structure. So if these vector spaces have an inner product, then for this matrix, you also have an adjoint matrix. You can basically use the transpose of this matrix to move things backwards, right? So if you have an edge feature or vector in the vector space of the edge, you just follow the kind of reverse of this arrow to move things backwards. Sorry, this arrow. So I can move things from E to U by just applying the transpose matrix, and I get another vector there. So this looks already quite a lot like this message passing we saw before. So essentially, if we kind of combine left and right actions, we can move features from V to U, right? So this will be kind of equivalent of a message between two neighbors in the graph. Basically, by kind of going through the intermediate edge, we are kind of transferring these features on like longer distances, and you can pass messages between nodes, essentially. So kind of the takeaway from this is that message passing are like group actions where the group is replaced by a graph. And you can kind of express this in kind of this sheaf or pre-sheaf terminology or view of things. So that's kind of an interesting connection between all these area of geometric deep learning and how you kind of have symmetries and acting on representations and things like that, and just graph neural networks. So that's kind of the view I'm taking in this talk. And I think this is kind of pretty much the end of all the math you're going to see, and from here is just gonna be applications and kind of following this this view to do some useful things. There will be a bit more math, but yeah, let's see. So in particular, I'm going to talk about this paper that was presented at NeurIPS last year. So this was a collaboration with Francesco Di Giovanni, Ben Chamberlain, Pietro Leo, and Michael Bronstein. So let me just get right into it. So the main application we looked at here was node classification. So you have a single graph, and let's say you have nodes coming from two classes, like spammer or non-spammer or something like that, and you want to separate these two, like classify them. So in this case, we have blue and orange nodes. And it turns out that the key metric when you have these kind of tasks is the heterophily of the graph. So what is that? It's a very simple metric. It basically expresses how heterogeneous the graph is. So how many connections between kind of differently labeled nodes you have as a fraction of the total number of connections you have in your graph. So basically, if you have very high heterophily, it's more like an opposites attract kind of network. And there's a very interesting phenomena that people observed when they apply GNNs to these graphs. The more heterophilic the graph is, the worse kind of your performance gets. And this is not true completely for all the graph neural networks, also because people noticed this and started to make GNNs that could fix this problem. And this is also what we're going to do in this talk. But kind of the graph neural networks that people have used for many years and have been quite popular, they often struggle in this setting, and you're going to see a plot like this. So that's one problem we're tackling.
Sorry,
another.
Can I add a question?
Sorry.
So
yeah, sure.
This heterophily, so this is a global measure of the whole graph, but you could also define this for every vertex, so it would become a vertex measure. Is that ever done, or is it usually always just a global measure of the graph?
Yeah, there's all sorts of metrics for heterophily. I think the one I'm showing now is the most simple one, but there's ones like doing what you said. There's kind of looking more locally, how many of your neighbors are different and things like that. So there are also more local metrics if you want, and they can get quite tricky. But just to keep things simple, this is the easiest one.
Okay.
Also, just to clarify this kind of classification problem, because I
Yeah.
work with this generally. So what is your classification problem like? You have a subset of the nodes that are labeled and you want to extend to the whole graph, or you want to go from one graph to another of the same type?
Yeah, good question. Yeah, I should have clarified that. I think both are possible. In this context, just a subset are labeled. So in all the experiments, you're going to see just a subset of the nodes are labeled, and then you want to label also those that are not labeled yet. But you can use you do have the features of the nodes that are not labeled. So it's called semi-supervised setting. So you can use the features of whatever is not labeled, but obviously you don't have those labels, so you have to predict them. Yeah, good question. Any others? All right. Now, a related problem to heterophily is oversmoothing, which again affects a very large family of graph neural networks. So especially in this message passing family. So people notice that if you actually stack up many message passing layers, like the ones you've just seen, the deeper you get, the more layers you add, the features become smoother. And by that, I mean, as you kind of move from one node to another, the features will vary just by some tiny amount. So they'll be very similar. And in the extreme, all the features in the graph will be the same, basically, which is obviously bad, because if you want to separate these nodes, you want to have like different representations for different classes. If all the vectors are going to be the same, obviously you can't separate them. So this is another problem which we're going to look at through the lens of sheaf theory and sheaves. Okay, so now here's a potential intuitive understanding of what's going on for these two problems, or maybe let me show better say like a pathological example which suffers from these two problems. And that's just heat diffusion. So this is a very common process in physics. It has this equation where this delta here is the Laplacian, the graph Laplacian. So this is a discrete diffusion process. It's like a discrete version of what you see like in Rn or whatever, or on manifolds. And we can discretize it in time. So this is just an Euler discretization. It looks like this. And qualitatively, it looks like in this picture. So you have some nodes, obviously, and connected by edges, and then you have some temperatures. So this is just scalar features associated with each of these nodes. You have some cold nodes, some hot nodes. And as you kind of evolve this process, the temperatures will kind of tend towards equilibrium. So you see cold nodes become warmer, warm nodes become colder, and until they reach this kind of gray equilibrium and kind of zero temperature. And this kind of suffers from both of these problems. I was showing you this kind of process, right? Like all the representations become the same at the end, all the nodes converge to the same temperature. And actually, if you have more connections between, like if your graph is very heterophilic, you're going to have very rapid transfer between this kind of cold and warm regions, and things balance out much more quickly. So actually, you can see how if you're in a heterophilic graph, it will suffer even more from oversmoothing. So it's quite interesting in this toy model how things interact. And you might ask, okay, what does this have to do with graph neural networks? And actually, if you look at one of the most popular graph neural networks, that's the graph convolutional network. It has this equation. So here, A is just the adjacency matrix of the graph. D is a diagonal degree matrix. So it's just a normalized adjacency matrix. You multiply this by the features and some weight matrix here. You can actually massage these terms slightly, and you're going to see we recover this red part at the top. So in some sense, the graph convolutional network is a bit like a discrete diffusion process with some added nonlinearity. So this sigma is a nonlinearity. And you also have a weight matrix, but it's kind of a wrapper around heat diffusion. So in some sense, it's not really surprising that it actually suffers from oversmoothing and heterophily. And actually, this nonlinearity and weight matrix you put there does not really change much. You can show mathematically. But this is just the point is that they're quite similar.
I have a question. Going back, maybe even a slide, and then maybe also tying into this one.
Yeah.
So I think I'm just like not understanding the setup quite right, in the sense of I was thinking of message passing happening on a fixed graph. And then I don't know how to think about layers associated to that. Like, should I think about sort of unwrapping the message passing in time so that I'm like thinking of copies of my graph over time as my layers? Or is there a different like deep network going on here that I don't know how to associate to the message passing?
Yeah, I think you're right if I understand correctly. So your graph never changes. It's at least not for this talk. So the graph always stays the same. It's only the features associated with the nodes that change from one layer to another. So basically, for instance, in this graph, it's the same from here to here. What changes is only the kind of the features associated with the nodes. So you're going to go through this process, update the features of node V. This will also happen for all the nodes around. I'm just showing only one node. So you have new features now, and now you just repeat these. So imagine having one more arrow here, same graph, but new features again, and so on. So
the layer I can think of as like state of the network at some point in like after some number of updates of message passing.
Exactly. Yeah.
Okay. Thanks.
Cool. Any other questions? Yeah, and also something that maybe it's sort of alluded to in this comparison I was making here. You could also equate these layers as kind of a discrete version of time. So you have this continuous physical process. You could imagine it as a sort of continuous message passing between nodes happening in this kind of heat diffusion. And when you discretize it, you get kind of discrete message passing. So maybe that's another physical way to think about it. Okay, so what we're doing in this paper is looking at how can we fix this problem, essentially. How can we enhance this toy model so it doesn't actually suffer from these problems? And the way we do that is essentially replace the heat diffusion process with a more complicated diffusion process, and that's sheaf diffusion. So if you have a sheaf structure on top of your graph, you can define a sheaf Laplacian operator. So this operator generalizes the usual graph Laplacian that people use. And you can have a exactly similar symbolic equation, essentially, because the Laplacian kind of has the same property. So this is still a valid diffusion process. So how does this Laplacian look like? So again, a very simple graph here. And it looks kind of like this. So it's a block matrix. So that's the first difference compared to the usual graph Laplacian. And you would have d by d blocks if your vector spaces are d-dimensional. So I'm assuming all the vector spaces for all the nodes and edges are d-dimensional. Then the way to move basically vectors from to neighboring nodes is a d by d matrix. So these will be the off-diagonal entries. And how do you do that? Well, it's the combination of these left and right actions that I was showing, which is essentially a composition of two matrices. So you have the first matrix that moves things to the edge, and then you have the transpose matrix that moves things to the other node, essentially. And then there's also a minus coming in this definition. But this is where these matrices come from. These are the matrices that transport features from node Z to node U. And then you also have some, to get the valid Laplacian, you have some diagonal entries that look like this. And just to see that this generalizes the usual graph Laplacian, where you have basically one by one matrices. All these matrices are just one, essentially, so just the scalar one. So you just sum over all the neighbors of node V, and then you get the degree here. So the result of this summation is the degree. So you have the degrees of the nodes on the diagonal, and then you're going to have a -1 here for the off-diagonal entry. So that's the usual Laplacian, just to see how it generalizes this. Also, another difference now is that because it's a block matrix, it actually operates on vectors, so not on scalars, essentially. So you can have these vector features, and for each node, so these match the colors of the nodes, and you can also have multiple feature channels. So you can have multiple copies of these things. So this is kind of how it looks in this sheaf world. And actually, as I was alluding before, we can also see this new physical diffusion process as some sort of continuous GNN that evolves continuously in time. So you have this continuous message passing, but we're going to discretize it in a second. Okay, so now you asked, okay, well, do you have a nice picture for how this new diffusion process behaves? For heat diffusion, we've seen the kind of heat transfer picture, which is quite clear. It's a bit harder to visualize things in this setting, but one geometric way to think about this process is kind of analogous to manifolds. So this kind of message passing between nodes enhanced by the sheaf structure are kind of analogous a bit with parallel transport in differential geometry. So you could think of these vector spaces at each node as kind of a tangent space to the manifold at that point. And these matrices that we compose are essentially a way to transport vectors from one tangent space to another tangent space. So we could think maybe as a graph as a discretization of the manifold, or kind of these points in the graph being sampled from a manifold. And then when you kind of perform diffusion, you essentially diffuse a vector field over the manifold according to the geometry of the manifold. It's still quite abstract, and but it's one way to think about it. Another way to kind of see what the sheaf structure is doing here is like kind of equipping the graph with a more complicated geometry, such that when you do diffusion, you get more interesting behaviors, or you don't just have this very simple heat transfer. You can have more interesting effects happening through your network as you evolve the features, and we're going to see just that. Okay, so maybe another way to show you how this qualitative looks like is to just show you a video. So these are nodes and a graph, obviously, and then these are the classes, the colors, and the position of the nodes are their features. So that's, you see in the beginning, all the nodes are very much entangled because they've just put random features to everything. And it looks like everything's inseparable. But if you have the right sheaf structure, as you diffuse these graph, these features, you can see how all the classes get nicely separated, and then you would be able to classify them. Of course, I cheated here a bit because I knew exactly which class each node has, but kind of this shows how you can get some nice separation of the classes if you have the right sheaf structure and you perform this diffusion process. So this is just to see how it looks like.
Just to follow up on this,
yeah.
So these actions that you have are a choice, yeah? They're not a given of your problem. You have to
they depend on the sheaf structure you have. So basically you need to have these linear maps between vertices and edges, and none's giving you that to you for at least for a machine learning task. And we're gonna get to how we fix that in a few slides.
Okay.
But yeah, that's a good question. So none gives that to you. I guess if you do mathematics, you would consider some interesting sheaf structures, but in a machine learning setup, no one will give you this sheaf structure. Okay, so switching back. So this is just some pictures of what you've just seen, but just for 3 classes, how things get nicely separated. And this is not just a coincidence. So we have a result in the paper showing that for any node classification task on a connected graph, there's always a sheaf structure that can linearly separate the classes. I should also add for almost any initial conditions. So it doesn't, so it's for a dense subset of initial conditions. So basically pretty much anything, by performing diffusion infinitely long. So if you, in principle, this shows you can always find a nice sheaf structure that kind of solves your problem. And in essence, by sheaf structure, I mean a graph neural network. So that's kind of the point I'm trying to make here, that sheaves and graph neural networks are pretty much, 2 sides of the same coin. Okay, so as the previous question was just kind of showing the painful point here is that you don't have the sheaf structure. So who knows what's, this shows there is something like that, but who knows what that something actually is. And what we're actually doing here is to learn the sheaf structure. So that's kind of our solution. So let a model learn this geometry on top of the graph such that when you diffuse, you'll solve the problem. So how do we do that? Well, let's remember that all these nodes have some features. So I'm showing here, so for the orange node, there's this orange arrow showing the feature of node V. For this blue node, there's this blue arrow showing the vector feature of node U. And what we do, we just pass these two vectors through a neural network. So this is just a multi-layer perceptron. So you take the feature of node V, the feature of node U, and you concatenate them or something, and you pass them through like a neural network. And this will give you this matrix, which is kind of what we need to have a sheaf. So this is the matrix that moves features from here to here. And then we also do the same, but we just swap the order of these two arguments. So first we pass U and then V, and we get another matrix here. And now we've got everything we need. So that's pretty much all you need to have a sheaf structure. The vector spaces are kind of implicit. You just need to define these matrices, essentially. So the way we do that is just this neural network is a matrix valid function. So we'll just output the matrix. So now you have these matrices, you know how to move things around. And you can construct a sheaf Laplacian. You have everything you need, basically. And I just want to, and then we can basically perform the diffusion process. And I want to show some similarity between this and these graph attention networks or transformers, which are very popular architectures in machine learning these days. So what this family of models are doing is for some feature X, they learn an attention matrix X, which kind of does some sort of anisotropic diffusion. So it kind of says, I'm aggregating my neighbors with some weights, like a convex combination. So this is what this attention matrix is doing. And it's learned based on the features. Now, in this kind of new world, what we're doing is we learn a sheaf Laplacian based on the features. So it's just a different kind of matrix we put there. But algorithmically, it looks very similar. Obviously, this is a bit more advanced in a sense because you learn a linear transformation, not just a scalar combination of your neighbors. You learn how to linearly combine your neighbors. But yeah, I just want to show this in case it helps. Okay, and let's see some results with this kind of model. So first, in a synthetic setting, we have just a bipartite graph. So that's as heterophilic as it can get. So just two partitions, and you only have connections between the two partitions. And what we're doing here, we are checking, okay, let's learn a sheaf. We use all vector spaces have dimension 1. And let's just learn the sheaf and perform diffusion, essentially. And the sheaf is learned by just back-propagating through the diffusion process. So essentially, you learn the sheaf that gives you highest accuracy on this class. So that's kind of where the gradients are coming from. Basically, learn the sheaf that maximizes the accuracy of the model. And then as we kind of diffuse more, you can see this is the orange line. The accuracy generally gets better, and we reach somewhere around 100% accuracy on this toy task. Now, when we do just regular graph diffusion with some weights for the neighbors, so this is kind of just heat diffusion, essentially. So the blue line is just heat diffusion. We know we also have some results showing it can't actually solve this task. Yeah, heat diffusion. And that's kind of consistent with what we observe. So the longer we diffuse, actually the performance drops. And then we also know, if you actually look at what the classes are, and you can manually draw a sheaf, like you can manually write down a sheaf that actually solves this toy problem. And this is what the oracle green line is showing. And you can see after a bit of diffusion, it already jumps to 100% accuracy and it stays there. Obviously, like in practice, we're not that's kind of an upper bound because you never know the actual classes. And actually, how this sheaf looks like is quite simple. You would just need to ensure, actually, let me go back to this slide, yeah. All you need to ensure is that this product here will be -1. So all your matrices are 1 by 1 matrices, so you just have scalars. And if you have a -1 here, what you're going to do is kind of you polarize the neighbors to have opposite features. That's what that causes. It causes a polarizing effect. And that's how you kind of can separate the two partitions. You just they will have opposite signatures, essentially, at the end of the diffusion. And we actually looked at, okay, we learned this sheaf here, so let's see what did it actually learn. And if you actually look at these transport maps, they're pretty much all negative, as predicted, basically to enforce this polarization. So it learns this kind of negative weighting for the edges, and that kind of polarizes these two communities. You're also going to see some peak around 0. And that's because if you have like a 0 transport map, you kind of prune the edge. So that's also kind of a valid solution. You could prune a few edges and to stop communication. And that's still kind of a partially valid solution. So essentially this sheaf Laplacian that the model learned automatically by just following gradients is actually a sensible one for this problem. So it learned something reasonable that we would expect. Obviously, it's harder to check for complicated real-world examples, but and that's why we kind of try to have these small toy setup. But we also went for some more real-world networks that are heterophilic. And here you see these the homophily levels. That's the opposite of heterophily, and is ranging from small to high. So things are more heterophilic on the left side, basically. So lower scores means more heterophilic. And we had like a few variations of our model depending on the type of matrix that you would learn for these transport matrices. So you could learn a diagonal matrix, you could learn an orthogonal matrix, or just a general matrix with no restrictions. And the color coding, I think here, the red is the highest score, blue is the second, and then purple is the third highest. In general, the orthogonal matrices work best, also because they have more numerical stability. They're a bit easier to normalize the sheaf Laplacians when you use orthogonal matrices. And also it kind of enforces some sort of regularization, so you don't need as many free parameters because orthogonal matrices have some constraints on them. So that seemed to have worked best, at least for the setting we consider. But yeah, in general, this family of models we've designed here were outperforming all these kind of previous GNNs, where most of the ones at the top have been specifically designed to kind of fight with these two problems with oversmoothing and heterophily. So this is kind of a nice way from going from all this theory to something that seems to work in this setting. All right. Yeah.
Can you tell us something like what is the data? For example, in this Texas data, what is the data? What is the classification task here? Give us some information.
Yeah, good question. So I need to remember this, but okay. So there's kind of 3 groups, I think, of data sets in here. So it's a combination of actually multiple sub data sets. I think, so for instance, for film, there's a network of actors, I think, and in what movies they collaborated with other actors and things like that. So it's something of this kind. I think Squirrel and Chameleon are taken from by kind of crawling Wikipedia and following kind of links on some, I think, from families of squirrels and things like that. I can't actually remember. Yeah, so it's that kind of data. CiteSeer, PubMed, and Quora are kind of social sort of networks. So CiteSeer is like a citation network. I think Quora, similarly, PubMed is also citations between, I think, some medical journals, papers, something like that. Yeah, I don't remember more details, but that's kind of the feeling, the general feeling of the data.
And then what is the classification task? Like, let's say the film network. What is the code classification then the task here? Right.
I think it was potentially classifying the actors by kind of movie genres or something like that, if I remember correctly. But yeah, in all these things, you need to classify the nodes of these networks. I think also for Texas and Wisconsin, they might be kind of some student dorm kind of networks between students and things like that. I can't remember actually what the precise classes were. I think it might be what they were studying and things like that. So yeah, I think it's been a while since I touched these data sets, so I don't remember the specific details. Sorry about it.
No, yeah, but that's answered my question. Thanks.
Oh, yeah, good questions.
So it looks like for this social groups, social media or whatever, the network, the learning performed is worse than for the rest of them. Can you speculate on why is that happening?
Yeah. So all these kind of 3 data sets, I think it's a combination of multiple factors. So all these 3 data sets are kind of the classic high homophily data sets that people use for kind of testing GNNs. Is kind of from the early days of GNNs, is kind of been the main data sets that have been used. So one factor is that people have hyper optimized for these data sets since they've been around for kind of a long time, and it's kind of the main ones people go to when they kind of do some quick prototyping. The second one is that kind of the classic family of GNNs do well on this just because they're homophilic, and they have this kind of implicit assumption. That was kind of one of the implicit assumptions of early GNNs, that the networks we're going to pass are kind of homophilic, and if you do a bit of kind of diffusion on them, you're going to improve the representations. So they kind of have this assumption baked in, and obviously they will do, they have a higher chance of doing better on things that kind of agree with this assumption. Whereas in our case, the assumptions are kind of weaker. So we have a more general architecture, which should be able to adapt to multiple settings, but of course is less aligned with any of these settings independently, right? You kind of have to learn these things from data. What kind of network is this? Should I be more kind of prepared for heterophilic interactions or homophilic and so on? So I guess having a more general architecture has less chances than one that's specifically designed for that. So I think these would be kind of the main 2 factors I believe here. But despite of this, I think the model was still, I think on 2 of these models were still in the top 3, so it's still kind of a reasonable assumption, reasonable performance in that setting as well.
Thank you.
Thanks. Yeah, good question. Any others?
Hi, I have a question. So previously you explained the similarity between graph attention network and then your shift network. So I'm wondering why this graph attention network is not performing very well on these data sets. Could you explain a little bit?
Yeah. Yeah. So there's been some follow-up theoretical work also showing that graph attention networks actually are, why they're not necessarily good in these heterophilic settings. So there is already some kind of theory in the literature. I think at the time we were doing this paper, people knew pretty well they don't work so well in practice in these heterophilic settings, at least not without some modifications. And I think maybe one intuition is that you could think of what graph attentions are doing as a variant of the diffusion process, where you kind of weight your neighbors by this kind of convex combination. So you can put more weight on certain neighbors than others, and it's actually a discrete version of what's called the I think it's anisotropic diffusion. Basically, you can diffuse more from one neighbor than from another neighbor, essentially. But it's still kind of a diffusion kind of process, like a heat transfer kind of process at the end of the day. So that'll be my intuition. But there's as I was saying, I think there's more advanced theoretical arguments for why that's the case that have been proposed.
Okay, thank you.
Yeah, good question.
Hi, could I ask a question?
Yeah, sure.
Yeah, so I just want to step back a little bit and check my understanding. The time step number in what you're showing, is that the analog for the layer number in, say, a GCN?
You mean kind of in the earlier slides with like heat diffusion?
Yeah, that's right.
Yeah. I use them interchangeably. Yeah, so time step is layer, basically. Yeah.
Okay, gotcha. And then, so another just question to check my understanding. In the video that you showed, I think what I understood is that the position of the nodes were the original features.
Yeah.
And then as that video evolves and the nodes move around, is it the case that you're showing us now the new latent representations of those features?
Yeah, exactly. It's how the features evolve from one layer to another. Yeah.
Okay, gotcha. And then, sorry, maybe just one more if you don't mind. So in a normal diffusion problem, right, we're diffusing some kind of scalar. Maybe it's temperature, concentration, or something like that. Yeah, maybe you said this, but I just missed it. What's the quantity we're actually diffusing in the method you're showing us?
Yeah. Okay, maybe I can go back to the GCN equation. So, okay, if we look at just the stuff of the lost equality, if you just multiply the first two matrices essentially, so this diffusion operator and X, the feature matrix, basically that would just kind of diffuse independently each column of X. So because the Laplacian operates on scalars, right? So you could think of each column of this X matrix as a kind of column of temperatures. So you have multiple columns of temperatures, right? And you kind of diffuse them separately. What makes you not to diffuse them separately is that you also have a weight matrix that takes linear combinations of these kind of temperatures. So it's kind of like each node has multiple temperatures, and this weight matrix mixes these temperatures, right? And this left matrix, it just diffuses each column kind of independently. Does that make sense?
Oh, right. Yes, absolutely. Yes. So the key is that we're moving from thinking about diffusion as a process that spreads out a scalar to a process that moves around a vector. And
yeah, exactly. Yeah, exactly. So now what kind of change is like, instead of, one column in our case is no longer formed of scalars, but formed of vectors. But as before, you could have multiple of these columns, some feature channels essentially. And now you diffuse vectors. So if basically this matrix, when you multiply it with this other matrix, it will independently diffuse each of these columns. But because we also use a weight matrix like here, we are also mixing these vectors as well.
Right. Okay, yes, thank you so much. I appreciate it.
Yeah, good questions. Hopefully then clarified. All right, any other questions?
I have a quick question about the...
Yeah, sure.
The dimension of the vector spaces in your experiments. So normally, how do you choose the dimension of the vector space over vertices? And even as a follow-up question, while learning the sheaf Laplacian that gives the best accuracy, do you fix the dimension or do you allow the dimension to change and find the best dimension for each vector space?
Yeah, good question. So we treat the dimension as a hyperparameter because it's hard to learn it automatically because it's kind of like a discrete operation, an extra dimension or not. And I think we use up to 8 or something like that as the highest dimension. You also run into some other kind of complexity issues if you have more than that. And I think we're also overfitting on these kind of smallish data sets with more, basically also have more flexibility as these things get bigger. So I think, we use somewhere between 2 and 7, 8 in general, and it was a hyperparameter basically. So whatever gave us higher validation accuracy, we use that.
Okay, thank you so much.
Thanks. I do have a last section, so maybe let's go through that very quickly and then we can take more questions just to make sure I finish it. It's very short. I just wanted to basically show you some follow-up works, and I'm just going to mention them briefly. I'm not going to go into the details, but just to see, the many kind of ramifications of these ideas that have been tried. So something that you could do instead of learning a sheaf Laplacian like we did, is to kind of build a Laplacian at pre-processing time just from features. So instead of always learning this and backpropagating through your layers and these gradients, you would just learn a fixed Laplacian from the features at pre-processing time and use that all the time and never changes. And the way we did that in this paper was to essentially, there's this algorithm from the connection Laplacian paper. So this is a quite popular paper. It's the connection Laplacian on graphs. I think it's from 2007 or something like that, maybe. And they have they show when the graph is kind of sampled from a manifold, they have a very nice algorithm for generating a connection Laplacian, which is basically a sheaf Laplacian with orthogonal maps. And we kind of adapt this algorithm for our purposes, and it actually it works quite nicely in practice, even when your graph doesn't came from a manifold, or we can just assume it does. But so it's not necessarily very rigorous theoretically, but it works kind of quite nicely in practice. And the kind of gist of the idea is to kind of approximate some tangent spaces around each node based on the features around that node, and then find the orthogonal matrix, this transport matrix that you have on the off-diagonal entries of the Laplacian that best rotates this tangent space into this tangent space. So it's basically the connection Laplacian associated with the manifold this graph came from. That's kind of the idea, assuming that actually happened. Another idea is because attention has been shown to work quite well, and it's a very important inductive bias, and people use it everywhere. We could combine it with what we were doing, and instead of just learning these kind of transport matrices between two nodes, we could also learn an attention coefficient. So we could have a combination of this sheaf diffusion and anisotropic diffusion, and that also works quite nicely, and it gives you some extra flexibility because the sheaf Laplacian is always a symmetric matrix because it's a Laplacian, but if you also have an attention matrix, the attention is not symmetric in general. So you have kind of this asymmetric diffusion operator that kind of gives you some other properties, and that also works quite reasonably in practice. Another thing we tried was to look not at the diffusion equation, but at the wave equation. So it's very easy to get a wave equation on sheaves as well. You just put an extra dot here on this equation, and you get the wave equation, and that also works reasonably. We have like kind of fewer theoretical arguments for why this would actually work, or unlike with like sheaf diffusion, where I think we had some quite reasonable theory, but this also works in practice, not as well as sheaf diffusion, but it works reasonably well. Another very recent work, so this was just accepted at a workshop at NeurIPS, and it was done by Hei Yu, whom I supervised for her thesis. So here, an important problem in graph neural networks, or like in this transformer world, is how do you kind of encode position as a feature to your model? And people use this kind of graph Laplacian positional encodings based on eigenvectors of the graph Laplacian. So we just generalize that to the sheaf Laplacian, and you can at the same time learn these eigenvectors because you can learn the sheaf Laplacian. So you can kind of learn these positional encodings. So the algorithm is quite simple. So you have a graph, you construct some sheaf Laplacian, either you learn it or you pre-compute it, as I was discussing earlier. Then you compute the eigenvectors of these things. So you just get some vectors, and then you just augment your features that you have for your nodes with these kind of positional encodings that come from the sheaf Laplacian. So then you kind of have some knowledge about, how is this node placed in the wider context of the graph? What is its position in the graph? And you can also backpropagate from this whole process. So you would send this matrix then to your favorite graph neural network, and so on, and you can send gradients through all this process and learn a Laplacian that helps you solve the problem. So there's also some interesting work that you can find online. Also, I want to highlight this work. I was not involved in it, but it's coming from my colleague Julia Dutzer, who and my former advisor. So they extended sheaf neural networks to hypergraphs in quite some smart way, and they also consider nonlinear versions of this Laplacian. And then they do some very kind of analogous things on data science problems or machine learning problems on hypergraphs, and they obtain state-of-the-art results on many problems. So again, this kind of worked quite nicely there. And finally, there's also my PhD thesis, which is online, and it covers much more than sheaves. It also goes on kind of wider interactions between topology and machine learning. So again, if you want to put this, to put this in even wider context, check it out. And yeah, that would be it. Thanks a lot for your attention, and for the questions.
I'm so sorry.
Yeah,
man. So
okay, I think that was a background noise.
Yeah,
but thank you, Cristian, so much for your great talk. We can everyone now unmute and clap.
Thanks a lot
to Cristian. And do we have any questions?
I was wondering if these models and especially the ones that you introduced later, are available on PyTorch or, as a easy to use package right
Yeah,
now
I think,
or in the future?
yeah, our main paper is on GitHub, so it's in PyTorch. For the follow-up works, I think not all of them have open source code, so they have been done by my collaborators. I think not all of them have been open source, but yeah, I think the kind of main ideas are kind of in the main paper, and I think the sheaf hypergraph one from Julia, I think probably it will have some code online soon if it doesn't have already. So yeah, there's quite a lot of code online already to kind of get started. Yeah.
Okay, thank you.
Thanks.
Okay, I think Georg raised a hand first, so go ahead.
Hi, thank you very much. Very, very nice talk. I missed the beginning, so I'm sorry. But I was interested in what you said about the wave equation in the sheaf context. I was wondering if you could say a little bit more specifically about how you handle stability problems.
Yeah, that's a good question. I think we haven't thought that much about it. One way to handle that is not to evolve it too much, so kind of limit time. And another one is just to use like some other tricks. Maybe you can just normalize your features every now and then and things like that. Just kind of hacks. I guess it's not like necessarily the most principled way to do it, but yeah, I think that's one of the reasons. I guess it's less nice theoretically also to work with. But I think with many kind of deep learning ideas, they just work. I guess if you pass gradients and you parameterize your things in the right way, it just works. So I think that's kind of what happened here. But yeah, I think there's definitely a lot more questions to be asked here theoretically, and like the ones you asked. I think yeah, it's a good question.
All right, thank you very much.
Thank you.
Zidhard, you are raising hand.
Yeah. Hi, Cristian. Thanks a lot for the great talk. I had maybe a little bit of a naive question, but it sounds to me like the structures that sheaves sort of impose on machine learning tasks, particularly requiring sort of this linearity between the features that exist on the vertices and the edges. I just wanted to sort of understand like how sort of restrictive is that? Like, I mean, like, can you go beyond sheaves in terms of like nonlinear diffusions happening on graphs and things like that?
Yeah, good question. So I think one thing that probably I haven't made super clear in the talk, because I haven't actually put the discrete model we use in practice on the slide, but we actually use kind of maybe I can show you the GCN equation because it's very similar. So we do something in practice. We have like a nonlinear version of when we discretize. So you can replace this delta here with a sheaf Laplacian delta. So you just replace the Laplacian essentially, and you have like a very similar structure here that also has nonlinearity. So even if the message passing is linear at the end, you apply nonlinearity at the end of the layer, so that makes it nonlinear. So that's kind of the easiest way to add these nonlinear effects. But yes, there's nothing constraining you to. And actually, I think when I can't remember actually how we parameterize these function here, but for instance, even here, you could have a nonlinear. I think we use a nonlinear function here to learn, like the matrix valid function is nonlinear as a function of VNU. Of course, that then you apply this to VNU, so in that sense it's linear, but it's still a nonlinear function of the feature. So there's multiple kind of places where you can add nonlinearities in this framework, and we do. Yeah. Did that answer the question?
Yeah, that did. Thanks a lot.
Thank you.
Mehmet, you have a question, go ahead.
It was a very interesting talk. Thank you so much. You already addressed a little bit about computational complexity of these, calculations, and you said you went up to 8 dimension, right? Even up to 8 dimension is right, still computationally very expensive. Did you do anything specific to solve these complexity issues for sheaf Laplacian case?
Yeah, I think so. The complexity of this is quite nice actually, as long as you stay in a relatively low dimension. So there's a d squared factor. I think yeah, it might be d cubed. I'm not sure. I think from top of my mind from these vector spaces. But in general, you can treat as kind of a constant hyperparameter in a small range. And if you actually want, that doesn't constrain you much, because like if you want to get like very, if you want to have a lot of features per node, you would just stack more feature channels, and that doesn't make your complexity explode. So actually, assuming this d, if you treat it as a constant, the complexity is pretty much the same as for GCN, the graph convolution network. So it's linear in the size of the network.
Okay, all right, thank you.
Thanks. Yeah, that's a good question.
Okay, I think we are now filled an hour, so I'll stop the recording now, and we can still stay for our offline conversation if anyone wants to. So thanks a lot, Cristian, for this talk, and thanks for all the questions and discussion.
Thank you.